Okay, so good morning. This is going to be the first of many recorded lectures for you to listen to at home, to take notes, and I hope this works and that I can upload and share this with you in due course. Okay, so moving on, we're going to begin Module 4 with Chapter 5, the lipids. So within this chapter, we're going to talk about the role of lipids in the body and in food, the physical and chemical properties and functions of the three classes of lipids, namely triglycerides, phospholipids, and sterols. We're going to be recapping the process of digestion and absorption of lipids and expand on our knowledge of transport of fats in the body. We're going to look at how fats are stored and used by the body. We're going to learn about blood lipoproteins and dietary fats and their impact on health, so things like LDL cholesterol, for example. We're going to look at the functions of essential fatty acids, i.e. the omegas, omega-6 and 3. We're also going to be exploring the process of hydrogenation, thinking about what are trans fats and what is their impact on health. By the end of this chapter, we should be able to identify sources of dietary fats, and we'll be discussing practical ways to reduce solid fats, i.e. saturated fats in the diet. So first of all, when we say lipids, we're referring to fats. We can use the term solid fats if they are solid at room temperature, such as butter. And if they're liquid at room temperature, we may refer to them as oils, so things like plant and seed oils, with a couple of exceptions. We already know that our diet must be moderate in fats. The AMDR advises us that 20 to 35% of total calories should be from dietary fats. And as I've already mentioned, there are three classes of lipids, namely triglycerides, which can often be abbreviated as TAG, phospholipids, and sterols. And these categories they're categorized based on structure and the components within the structure. So why are fats useful and what's their purpose? Let's first examine the use of fats in foods, so the right-hand column of the next two slides. So we know that fats provide nutrients in the form of essential fatty acids, as well as fat-soluble vitamins A, D, E, and K, and as well as other needed components such as fat-soluble phytochemicals. These nutrients and molecules are soluble in fat, thus their transport fat is essential. Examples of fat-soluble phytochemicals include the carotenoids such as lutein and lycopene. Carotenoids are best absorbed within a meal that contains fat. Also, chopping, pureeing and cooking carotenoid-containing vegetables in oil generally increases the bioavailability of the carotenoids they contain. So fat's also, of course, the most energy-dense macronutrient at 9 calories per gram. Fat also confers taste, flavour and smell to foods and renders them much more satisfying, hence sensory appeal. And by being more satisfying, fat-containing foods may help with appetite control. If we are satisfied and feel full after a meal moderate in fat, we should be able to keep going for several hours before feeling hungry again, hence satiety. So let's move on to fats in the body and the usefulness of those fats. So we know that fat provides us with a stored energy supply contained within our fat cells or adipocytes. This fuel keeps the body's processes ticking over at a cellular level, but also allows us to perform aerobic exercise and sustain this activity. So we also know that fat may be mobilised and metabolised to produce ketone bodies. Sorry, we haven't quite finished the previous slide. Which in times of starvation or severe illness helps maintain organ function, particularly of the brain. So fat also hence emergency reserve for energy. Fat also acts as protection. Subcutaneous fat stores protect our vital organs and act as shock absorbers, reducing potential damage from impact. Fat keeps us warm. A low percentage body fat can compromise your body's insulation, of course, and fat slows heat loss when it's cold and helps to maintain our internal body temperature. Lipids also have a crucial structural role within cell membranes, so fats form the major material of cell membranes in the form of phospholipids, and we'll be talking more about that in due course. And lastly, in this table, raw materials. So fats, as we know, can be converted into other substances in the body, such as bile, lipid hormones, and vitamin D, as well as other things as needed. So a couple of further points. This slide summarises what we've just covered in that table. A couple of points. So the first point, subcutaneous fat stores, i.e. your adipose tissue, actually secretes hormones that play a role in appetite regulation, such as leptin. Remember leptin? Another point, fat, owing to its high energy density, is the most effectively stored macronutrient. Think of glycogen. Glycogen is a water-soluble storage form of carbohydrate. Obviously, carbohydrate is water-soluble. Glycogen is highly branched, and as such, it actually holds a lot of water within, the molecular structure between the branched chains, making it much heavier and bulkier and less energy dense than fat stores. Okay. Figure 5.1, this actually illustrates a fat cell within the context of, your skin. Below the skin are adipose tissue, on top of our muscle tissue, as many of you will already know. And then this is enlarged here to show a fat cell in very simplistic form. So within the fat cell, lipids stored in, a droplet, you could say. And this droplet can greatly enlarge or shrink according to energy provision. The fat cell membrane will expand to accommodate its swollen contents, essentially. So really, we can't necessarily increase the number of fat cells that we have within our body, but the individual fat cells themselves will shrink or enlarge. And the arrows here represent lipid exchange from the blood, so entering or exiting. Okay, so how are fats useful in foods? This is expanding on that point. So figure 5.2 is telling us how fats are a concentrated energy source. Both lunches contain the same number of calories, 550 calories, but the fat-rich lunch below takes up much less space and weighs less because obviously fat is more energy dense than the other two macronutrients. So this is demonstrating how fat-containing foods are energy dense. The fat-rich lunch weighs 115 grams versus the carbohydrate-rich lunch, which weighs 500 grams. Okay. And also, as we've already mentioned, within food we find fat-soluble vitamins, namely vitamins A, D, E and K. This should be becoming more familiar with you, as well as the essential fatty acids. This slide we've covered in table 5.1, but to summarise, again, fat gives food flavour, texture and smell. Fat increases satiety, how satisfied we are from the meal. One reason that fat digestion is more complex is fat tends to leave the stomach last and therefore slows down the rate of digestion, increasing what's called the glycemic load of the meal. Okay, so this slide we're going to take our time through. So first of all, we're introducing triglycerides. What are triglycerides? Well, they consist of 3 fatty acids bound to a glycerol molecule, which can be described as the backbone. So the glycerol backbone here is illustrated, highlighted in yellow structurally. Glycerol is an organic, i.e. carbon-containing, small, water-soluble carbohydrate derivative. And triglycerides are the chief form of fat in foods and the human body. Very few fatty acids are found free, i.e. in individual sort of structural form. Most are incorporated into large complex triglycerides. Note that each of the 3 fatty acids bound to the glycerol backbone may differ in either chain length, that's seen, I don't know where my mouse has gone there, seen here, different chain lengths, i.e. the total number of carbons. So the carbons here are shown as the circulars, the dots here with bonds between them. So varying in chain length or number of carbons. And also what's known as the degree of saturation. whether this carbon-to-carbon bond, so this stick between the two balls, whether that carbon-to-carbon bond is saturated or not, and we're going to go into that in much more detail in a second. When a carbon-to-carbon bond is saturated, this means that the two open sides to the carbon are each bound to a hydrogen atom. In other words, saturation refers to whether or not a fatty acid chain is holding all of the hydrogen atoms it can hold, i.e. at capacity. Carbons have 4 positions to which other atoms, whether it's a carbon, oxygen, hydrogen, or another functional group like an alcohol group, can be bound or bonded to. Where the bond between 2 carbons is saturated, this can be called a double bond. A double bond or saturation results in a change in the shape of the fatty acid and thus the triglyceride. So let's have a look at that in the context of this illustration. So on the left, saturated fatty acids have no double bonds, okay? So each carbon here, all 4 of its positions are filled, okay? Whether it's to the next carbon, to the end, i.e. the glycerol backbone, and to 2 hydrogens that will be filled here, okay, throughout this chain. And what this means is that structurally, in shape-wise, a saturated fatty acid is very straight. Okay. We've heard of what are called monounsaturated and polyunsaturated fats. So structurally now, think of what I've just explained about a carbon-to-carbon double bond or point of unsaturation. So in a monounsaturated fatty acid, there is 1 double bond, 1 point of unsaturation. And you can see in this particular one, it's on the 9th carbon here, the 9th to the 10th carbon. All right, it highlighted in yellow. So what's happening here is that this carbon and this carbon have a double bond, meaning that the remaining 4 positions, so each carbon here, one of its bonds is going to that other carbon, and two of the other available bonds are between the carbon, so it's going to have 1 fewer hydrogen bound to it. And what that means is that it actually confers a change in shape and structure in that fatty acid chain. Polyunsaturated fatty acids have 2 or more points of unsaturation, 2 or more double carbon-to-carbon bonds, conferring even more of a change in structure and shape. Okay. So the more carbon atoms in a fatty acid, the longer it is, obviously the longer the chain. The more hydrogen atoms attach to those carbons, the more saturated the fatty acid is, as I've just explained. So think of this in real terms now. So the saturated fatty acid is long and straight, meaning in structure is more rigid in shape. So it's going to be solid at room temperature. So things like butter, shortening, coconut oil, okay? With an increasing degree of unsaturation, moving to the monos and the polyunsaturated, the structure of the fatty acid becomes more fluid in shape, so less rigid, more fluid. And this renders it to be liquid at room temperatures, things like olive oil, avocado oil, canola oil. Okay.